It works.
Doesn't jump by itself.
Yeah, I hope not. I don't know. I'm not very good at this.
You're trying to do something?
No,
that's
no,
your cell phone.
that's my
You're
cell
trying
phone.
to call Alex, your lecture is over.
He's still talking?
He's there, it's still, yeah. Alex is continuing his lecture. Okay, good. The last talk of today is by Van Book.
Okay, so thank you very much. It's always my pleasure to be here. So I will talk about some recent work with Terence Tao about universality of random matrices. And it was something that we have been trying to do for quite a long time, about 6-7 years now, but I'm quite happy now that we sort of close it more or less. So let me start with a brief overview of the talk, because I never gave a talk this long, so I need to prepare myself too. So I will go over the history and models of random matrices, and next list a few classical problems concerning, well, when we talk about random matrices, then the first thing you want to know is what are the eigenvalues of the random matrix. And I will present a few classical problems about this. The interesting thing here is that these problems not only are interested by themselves, they form a hierarchy. And so, if you solve some problem on a higher order in the hierarchy, then you solve everything below it. And the top problem seems to be to determine the limiting joy distribution of a set of k eigenvalues. And the k here are order, so you can ask about what is the joy distribution of the first and the 24th and the n over 2 eigenvalues, for instance. Okay. Then I will mention the notion of universality, and the reason is that it will be, well, people in mathematical physics mention this a lot, but this notion is a little bit different from that. In fact, it is quite, well, more general. The notion from mathematical physics usually talk about the universality of the k correlations, but we will talk about something more general than this. Okay, and then I will give a brief survey of recent results. And the highlight of the talk will be the presentation of what we call the four-moment theorem, which roughly states that the problem in the top of the hierarchy that we want to talk about, namely the joy distribution of any k eigenvalues, is determined by the first four moments of the entries. So the only thing you need to know is that the first four moments of the entries of the matrix, and you know everything. Okay, then the applications of this theorem. And another key point here is that, well, I mentioned four moments here, and with respect to this theorem, it is more or less best possible. But since we have a hierarchy, if you apply this theorem to problem lower in the hierarchy, you don't really need four moments. Usually you will need only 2 moments or 3 moments. For instance, for the problem of correlation function or the problem of the gap distribution between consecutive eigenvalues, the only thing you need the 2 moments of the entry, which usually given 0 and 1 by normalization. Okay. Let me see. Okay, so here's the model of random matrices. There are a lot of them, but I focus on well, actually I want to introduce only 2 and will focus only one of them. The first one is the so-called random covariant matrix. First, I think defined by Wishart, is that you take a matrix non-symmetric or non-Hermitian n by p, which have independent entries, and then just take the product of this with the conjugate. So you will have a symmetric or Hermitian matrix at the end, but the core of it is non-symmetric. And the second one, and this one is popular in statistics. The second one, which is popular in mathematical physics, is that you take Hermitian one with independent entries in the upper triangular. Right? And in all this model, I will assume that the entries are independent and normalized, namely that we have mean 0 and variance 1. Right? And sometimes people allow the diagonal to have different variants, but you can omit that technical point. Okay, so a brief history that where these random matrices come from. The first source of this that I can find is from statistics. As I mentioned, Wishart, 1928, maybe even before him. And people study this covariance, sample covariant matrix because motivated by problems in hypothesis testing. And the parameters they look at here is that, okay, you take this product H, which H transpose, you get a semi-positive definite matrix, and the eigenvalues are just the square of the singular value of the original one. So the question is basically studying of the singular value of the n by p matrix, which is non-Hermitian. The next one is, it's very proper to mention it here. It came from numerical analysis and particularly motivated by a paper of von Neumann and Goldstein in 1947. It was a very early stage of this subject. Actually, the subject was defined by the sequence of von Neumann and Goldstein. And what they look at is the computational problem of just inverting a matrix. So, and when you do the inverting, well, we know that, okay, if the matrix is non-singular, then it can be inverted, but they really care about the time and the accuracy of the operation, because when you do, say, Gaussian elimination, you have to truncate at a lot of, well, at almost every step, right? So, and how the truncation will affect the final result, it depends on the critical parameter that you say you open any textbook in numerical analysis, you can see it is called the condition number. And the condition number is just the norm of matrix times the norm of the inverse. So basically, if, as I said before, if we care about singular values of the random matrix, then we have to know the distribution of the first one and the last one. That is more or less equivalent to the problem of von Neumann and Goldstein. Okay, yeah, so, and it is something, and of course they ask the question, what happens if you choose this matrix randomly? So in the modern language, it is an example of average case analysis, but of course they didn't code this that way. Okay, and then Wigner came in the 50s, and he now considered Hermitian matrices, and he used eigenvalues to model the energy levels in nuclear physics, and it generated the whole, the whole subject, huge literature about this. Okay, and now it's the more recent motivations, connections. It's a random matrix is something that happened in a lot of fields. Well, it's in probability theory, of course, and it was play a role in spectral graph theory. We hear a lot around Princeton here about connection with number theory, the roots of zeta function, combinatorics, and computer science and data analysis, of course. Well, whenever the matrix come and you assume something random, then of course the issue come into that, understand the eigenvalues of this matrix. Okay, and in this only a very partial list of people involved in this project that least here. Okay, so in this talk, as I said, I introduced two models. I will mainly just discuss the first one, the second one, namely the Hermitian one. And I even simplify it a little bit. Namely, I assume it is a complex, it have complex entries. And when the ring and the complex part are independent random variable. And they have now mean 0 and variance half, because you have to add them to get variance 1 and so on. It is just a technical assumption. The main result, for convenience, the main result will hold for general model. It doesn't really matter. It is real or complex, and it also holds for the Wishart model. Okay, so let me now go on a few technical definition. You may just skip it, but let me mention it because I use this notation a lot later in the talk. So, so the entries will be, I will call them sometimes the atom variables. And I will do two kinds of scaling. The first one is that I scale down the matrix by 1 over square root n. And you will see very soon that y square root n. And the other one, I scale it up by square root n. And the reason is right here. We know that the largest eigenvalue of the matrix is of order square root n. Actually, it's exactly 2 times square root n. So after I do this, after I do the coarse scaling, I will put all the eigenvalue in the interval -2 and 2, and which is nice because it is the finite interval. And the fine scaling serves the purpose that I normalize the spacing between the consecutive eigenvalue to be a constant. And that is convenient if I discuss result concerning the spacing of the eigenvalues. It of course doesn't change any result at all. But yeah, so two important examples. It's very classical. One here is when you put a Gaussian, when we assume that the entries are complex Gaussian, and it is called the Gaussian unitary ensemble, GUE. And well, the reason is that the measure generated by this is invariance under the unitary group action, and the other one is just the reinversion of this called GOE. And typically, GUE is a little bit more well understood, and it's easier to compute with GOE rather than GOE. But in general, they are very well studied distributions, and people know a lot about this. Okay, so the main goal of the theory, as I said, is to understand the behavior of the eigenvalues. And in this talk, I will order them increasingly from lambda 1 to lambda n. And yeah, so let me start with a very old and famous result, which is the semicircle law of Wigner. The semicircle law say that, okay, after normalization, I put all the eigenvalue in the -2 and 2. So this eigenvalue will generate a measure there. And okay, so we want to see that how do they distribute in this interval. And Wigner result proved back in the 50s saying that it distributed according to the semicircle density function, which I wrote here. And it is best illustrated by this picture. So it is, so it's a semicircle, and you will, okay, so if we want to know the number of eigenvalue between, say, -0.5 and 0, it will be proportional to the area of under the semicircle and over this interval. So you can see that more percentage of eigenvalue in the middle than eigenvalue in the same interval but at the edge. Right? So it is not a uniform distribution. And also, so actually there are three pictures here. The green one is the ring semicircle function, And well, actually the blue one is sort of hard to see, is a numerical we did with Bernoulli matrices, where you just put the entries to be +1 and -1. The red one is when you just put Riemann Gaussian into the entry, and they really give you the same law. Okay, and the proof as well. Now it is the moment method. So if you want to prove that the Riemann measure, a limit of the Riemann, of a sequence of Riemann measure go to some limiting measure, you only have to check the moments of the measure. And the moment of the semicircle density function is very nice. They are the Catalan number. And so what Wigner used is simply the trace identity. So we know that the sum of the lambda will be the trace of the matrix. And if we raise O the lambda to the power k, it will be the trace of the matrix raised to power k. And if you take the expectation on both sides, what really come in here is that the trace of the power of the matrix can be computed combinatorially. It will boil out to the computation of certain kind of walks in the complete graph. And then the Catalan number pop up naturally. So that is one of the proofs. There are many others. Okay. Okay, so we understand the global distribution of the eigenvalues, and the main open problem is what can you say about the local information. Yeah, and so now let me, well, it is the general, sort of the general notion, the local statistics. So let me give you a few examples so that give you a feeling that what I meant by this. Okay, so one thing people look at quite a lot is the distribution of the gap between consecutive eigenvalues. Right? So you have n order number, it gives you n minus 1 gaps. Right? So you can ask that, okay, so how many percentage of the gap satisfy the property that is less than some number s? Right? So it will be a function of s, and you want, okay, so what is a function of s? It is. The next one is the k-pole correlation function, the behavior of the k-pole correlation functions, and I will define it explicitly later. The next one is that you can ask the distribution of the individual lambda I for any I. Right? So I give you an index, say n over 2, and you want to know, okay, what is the limiting distribution of lambda n over 2, namely the eigenvalue in the middle, or any index for that matter. And if you are more greedy, or we are more greedy, then you can ask the joy distribution for any tuples of indices I1 up to Ik. Yeah, so let me now show a little bit about one of the very well studied case is the GUE case. Now this case, in this case, in principle, we know the answer for all these questions because we know something very sharp here. We know if, well, now if we do not order the eigenvalue anymore, just look at them at the point in Rn, then actually there's an explicit formula for the joy distribution of these n eigenvalues. Right? So it is an exact formula. When Cn is some normalization factor that you can compute. And it is a consequence of the fact that this matrix, this model of matrix enjoy, well, the decomposition, if you do the spectral decomposition, and U here is a unitary matrix, then, well, we know that every symmetric matrix can be, or Hermitian matrix, can be decomposed like this when U is unitary and D is diagonal. And the wonderful thing is that the distribution of U and the distribution of D are independent. And that helps you to derive this, this equation exactly. Yeah, and then in principle you can compute the answer to all the questions I just mentioned by a proper integration over this measure, which is not easy, but there are very powerful techniques developed to do this. For instance, if you are interested in the von Neumann-Goldstein problem, well, the von Neumann-Goldstein asks for the distribution of the ratio between the largest and the smallest singular value. And the largest, you know that it is roughly 2 times square root n with a little error term. So mainly you want to know the distribution of the smallest singular value, which is just the probability that you don't find any eigenvalue in some small interval around 0. Right? And this you can write down as an integration over this measure. Okay. And using this, there are people who compute this explicitly. I mean, the explicit answer is not so important now, but it is computable. Okay. So if you have any questions, just let me know. Okay. And yeah, by similar idea, you can compute the distribution at the gaps. Right, so yeah, we have all these n minus 1 gaps, and we care that, okay, how many of them is less than some number s. Then we care that, okay, so now it will be a function of s, then we want to know that, okay, what is distribution in the limit here. Okay. So I mentioned the k-point correlation functions. And let me give you the definition. Well, in terms of probability, it's more or less the marginal distribution. So you have a distribution on n points of all the n eigenvalues, known order, then you just integrate out n minus k of them. Okay? So it's like the projection onto a k-dimensional subspace. But you have better feeling about this notion if I give you some example. So let's say the 1-point correlation function, and it is behave like a measure. So to understand the measure, you just need to understand the behavior of the measure with respect to O interval. Okay? And so we take this function, you integrate it on an interval I, then the meaning of it is just the sum of the probability that lambda I belong to I, which is just the expectation of the number of eigenvalues in I. Okay? So this is the better example, that if you take k equal to 2, right, and you want to know the behavior of row 2 with respect to a box I times j, then what it is just the number, the expectation of number of pair ij of eigenvalue where lambda I is in I and lambda j is in j. That's it. Okay, so that is the meaning of this notion. Yeah, and so typically what people want to know is that, okay, you take some test function and integrate it with respect to this measure and look at the limit, and you want to know the behavior of this. Right. It's, in mathematical physics, there's also a popular version when you ask about the local version of this question, namely the two questions before you consider all eigenvalues, right? But now you consider only the eigenvalues in a small neighborhood around a point U in the spectrum. So you know the spectrum is between -2 and 2, so you fix the point in there and just take a small neighborhood around this point. And you look only at those eigenvalues in this small neighborhood. Yeah, so you can ask about now the same gap question. Maybe now you don't have n eigenvalue in there, only square root n of them. You still want to know the statistic, right? And the same for the correlation function. So we have to redefine these things for them to make sense. For instance, you see that we have to normalize by the density function of the point U here, because the neighborhood of the same length will contain a different number of eigenvalues if you take the center of this at different points. Okay. Yes, so now the next question is that, okay, we have all this lambda 1 up to lambda n. You pick a number I, and you want to say, okay, we want to ask what is the limiting distribution of lambda I. And of course, we need to do the usual thing that you have to normalize it by subtract the mean and derive by the variance or by the standard deviation. The mean is sort of easy to guess because you know the density function, right? So I give you say an index r equal n over 2, then you say that, okay, the mean should be 0 because it is in the middle. But the variance is not that so easy to guess what it is. Okay, and in general, you can ask the same question for any set of, say, maybe 10 eigenvalues glued together. Okay. Yeah, so here's the hierarchy that I mentioned before. We know that if we can answer the k-pole correlation problem, then you can answer the gap distribution problem. That is just some combinatorial inclusion-exclusion argument. Also, if we know the k-correlation, well, let me recall the definition of the k-correlation function here. Well, the only thing we want to know is that, okay, so how it behaves with respect to the boxes. Then if we know the joy distribution, say, let's take the k equal to 2. If we know the joy distribution of any 2 eigenvalues, then you know every single term on the right-hand side, right? If you know the joy distribution of lambda I and lambda j, then you know the probability that lambda I belongs to I and lambda j belongs to j. Right? So if you can answer the last question, then you can compute every single term on this right-hand side, and of course you compute the term on the left-hand side. And then you answer the question about the k-correlation function. Okay? And this is a strict hierarchy. You cannot, well, it goes only one way, basically. And so the bulk of the talk, we will focus on this last problem, understand the joy distribution of any k eigenvalues. Oh, I don't see the watch. No, what time is it? I don't see anything. Oh, okay. Half an hour. Okay, so so again, that this part is, I already mentioned that for GUE and also for GOE, when the entries are Gaussian, we know the answer to all these questions, and they are sort of complicated that even to describe what the limiting distribution is, you will see that, well, things like the kernel come up a lot, and it is a reason because that the joy distribution of the GUE have a determinantal form, and then the technique will give you, the integration technique will give you this result quite naturally. Yeah, but never mind the explicit formula. Yeah, so yeah, I mentioned the notion from universality from statistical physics. It actually a little bit different, of different flavor, because yeah, one remark here is that if we talk about the correlation function and take the limit, then actually, and we talk about the local version when you take the just look at the small neighborhood around a point U. And there, the interesting thing is that the answer doesn't depend on this point U at all. It will be the universal answer. Anyway, so yeah, so it's also the answer for the gap distribution. That, yeah. And one more interesting statistic that was used a lot in application is the distribution of the largest eigenvalue, the distribution of the edge of the spectrum. And say if you take the smallest eigenvalue, which is about -2, and you normalize it by just adding 2 to it, and now the variance is not is actually turned out to be n to the minus 2/3, and if you, or the standard deviation, and now if you, after doing this normalization, it comes to a famous Tracy-Widom distribution, which come up in, say, the longest increasing subsequence problem in random permutation for quite unexpected answer. And Tracy and Widom also computed the limiting joy distribution of any, say, the first k eigenvalues for any fixed k. Now, yeah, I said something about the edge, which you have Tracy-Widom. Now, inside the bulk of the distribution, namely inside the interval minus 2 to 2, the behavior is sort of quite nicer. If you take an eigenvalue and normalize it, well, subtract the mean and divide it by the standard deviation, it will go to Gaussian limit. Yeah, it is a nicer list. Yeah, it doesn't have any kernel or any complicated things in it. It is go to Gaussian, and it is proved by Gustafsson. It's based on early work of Konstantin Leibowitz and Soshnikov. Yeah, and he also proved the same sort of similar result for the joy distribution of any k eigenvalues. Okay, so a thing people proved back in the 80s for the least singular value, etc. Okay, so now I'm ready to go to the next part of the talk, namely that to present this notion of universality. It is not one problem, it's rather like a meta-conjecture or sort of a phenomenon. And it is a phenomenon that say that, okay, we see a lot of explicit answer there, some of them simple, some of them quite complicated, and all of them are computed for the Gaussian case. And the phenomenon say that this answer should not depend on the fact that the entries are Gaussian. Right. So it shouldn't depend on the very strict distribution of the entries. And yeah, so as I said, in mathematical physics, it's referred to a little bit different things, but I will take this notion in this talk. Right. And people, well, if you ask a physicist, then usually they very strongly believe it because they say that, okay, this distribution should say something about nature. And the nature, you mean you take a law of physics, then it shouldn't depend on how precise you model the interaction between the atoms. It only depends on some very coarse description of this interaction. But I mean, the general law of physics should hold no matter what matters. If you want to take a more mathematical feeling about this, you can think of the central limit theorem, which is the easiest example. That you take sum of IID random variables and normalize it, it will go to Gaussian, no matter which random variable you take at the beginning, if you're given the mean 0 and variance 1. Right? Okay, so here's a few numerical evidence. So I take, for instance, we run a numerical computation for the gap distribution for the Bernoulli model and the GOE model, and they more or less give you an exact match. And there are a lot of computation like that, which is quite convincing. Okay, but theoretical results are very rare. It's very hard to prove anything because all the technique, all the result that I showed you before, it depends on the explicit integration over this measure, and that's it. There is nothing to move, nothing to modify there. So it took a while until we get the first result of this kind by Soshnikov in 1999, only 10 years ago. And he proved the universality of the extremal eigenvalue, so the one at the edge. And he, under the assumption that you have symmetric distribution and exponential tail. And it is, and it used the Wigner choice method because if you raise the eigenvalue to very high power, then actually the choice will be more or less dominated by the first eigenvalue. Right? And yeah, it boiled out to actually a nice combinatorial problem about computing the number of special walks in a graph. Some water here. Now for the gap distribution and the K-correlation, there is an interesting result by Johansson in 2001. And he proved the universality of a mixed model, namely that you can take an arbitrary matrix model, but you have to add a non-negligible Gaussian part to it. So your entry should be the sum of, say, 50% Gaussian plus 50% something else of your choice. And he can prove this. And the method, it heavily depends on the fact that even for this model, you still have some explicit joy distribution, not as nice as in Ginebra, but computable one. And he make a very clever argument to work with this distribution. Okay, and very recently, sort of parallel to our work, there's a series of work by Erdős, Yao, and many co-authors. Actually, there's maybe like 10 papers or something. I don't read all of them. So they prove the universality of the K-correlation function with a little bit averaging. So you allow the point u move a little bit and then average over this interval. And in the series of paper, they need some assumption on the entries, and the assumption get better in time. So in the first few papers, the entries need to be highly smooth. But later on, they can remove this. So I don't know actually exactly what is the state of the art now, but this universality of the K-correlation also hold in under now quite general assumption. With a little more averaging, but that's okay. Okay, and finally, let me mention there are other works on the different model, so-called the invariant models, when we don't have a formula like Ginebra, but we have something much more general, and there's a work of many people here, Dive and his team, and Pastor and his team, and Bleher and It, and so on. Okay, so now I'm going to discuss the new result, which is so what I call the four-moment theorem. It says, well, informally, it says that if we care about the joy distribution of, say, a K-tuple of eigenvalues, the only thing you need to look at is the first four moments of the atom variables. So namely, if you have two models, Mn and Mn prime, and if you want to compare these two joy distribution, you need only to compare the distribution of zeta and zeta prime up to the fourth moment. And if they match, and everything match, every statistic of the eigenvalues match. So from here you can derive all the universality result you want. For instance, you can derive the universality of the Tracy-Widom law using only two-moment assumption, and you don't even need the symmetry. Or you can again have the universality of K-point correlation and the gap distribution. Again, you need only two moments, not four. The four is only for the problem on the top of the hierarchy. Okay, so so it's a definition that what is a matching moment means in the complex K, that actually you need to look at the the mixed moment. So, but never mind. Just think about the ring case. That's enough. So the theorem say that you take two model of matrices. So you can, and they have this entry zeta and zeta prime. They all have mean 0 and variance 1. The only extra thing I assume is that they have bounded large moment, say the 10,000 moment is finite. And the key assumption is that all these entries, they match to all the 4, namely that all the first 4 moments are the same. And they should match place to place. So ij should match to ij here. But the different ij can have different 4 moments. It doesn't really matter. Okay. And then if you look at the joint distribution of any k tuples of eigenvalue, so namely the probability that this point in k dimension belong to a region D, then it will be the same probability as on the right hand side. Okay. Quantitatively, it's even bounded by a negative power of n. Okay. Yeah, so it answers the hardest question we want to study in this under this assumption. And so for instance, from here you can derive a general theorem about the Gaussian fluctuation. If you have a matrix when the third moment is 0 and the fourth moment is 3/4, which match the Gaussian one, then the eigenvalue have Gaussian fluctuation inside the bulk. And okay, of course, it's natural to ask that what about this 4 moment assumption? Can you do it with 3 or even with 2? And okay, of course, something bad here. It's just the absolute value sign. I sort of believe the 4 moment is needed, and what we can prove is that if we change the 4th moment, namely say there's a difference like some constant between the 4th moment, then actually for typical index, there's an expectation sign needed here, that the expectation of lambda I and the expectation of lambda I prime is shifted by a non-negligible number. So if here is some constant c, then you have some other constant c prime. Okay. On the other hand, if you apply this theorem for problem lower in the hierarchy, you only need 2 or 3 moments, and I will show a few examples. For instance, if you want to study the distribution of at the edge, the largest eigenvalue or the smallest one, such as lambda 1, first of all, we gain something there because, the fact that the distribution function or the density function is semicircle show that at the edge you have a bigger gap between the eigenvalue because the density function there goes to 0. And that gap actually saves 1 moment in the computation. So actually we need only 3 moments, but then we have an idea of Johansson that saves another, or a result of Johansson that saves another moment. So basically you need only 2 moments for this. So here's a corollary. If you want to establish tracy with them, then the only thing you need is that mean 0, variance 1, and bounded moment for some large constant c. You don't need, for instance, you don't need the symmetry as in Shosnikov result anymore. Okay. So for the gap distribution, similar result holds, and I will, under the extra assumption that the support of the entries should have at least 3 points, and I just take it to illustrate an argument. Later on, we will even remove these 3 points. So actually, the stronger result say that even this condition is not there. But let me take it as the beginning. Okay. The reason is that yeah, so how do you apply this four-moment theorem? Well, if you care about some statistic of Mn, then the only thing you need to do is to find some Nm prime that have the same four moment and where the statistic is already computed. Then you say that, okay, well, we just take the result there and don't have to do anything. And of course, one thing we can take is just to compare it with GUE because we know everything about GUE. But in principle, you can compare it with anything that when the statistic is already known, right? And here, in this case, for the gap distribution, you can compare with the Johansson model. Because the Johansson model is what? It is just you take 50% Gaussian plus 50% that anything you want. And you can change 50% to be any constant you want. So you have an extra degree of freedom. Right? And so it boils down to just a moment matching theorem. Right? So you have to find, so I give you a random variable, and you have to find three things, C1 and C2, and some sigma prime here, so that the Johansson variable here have the same four moments as your original. Right? And that is always doable. This is the truncated moment problem. That's classical one, first studied by Hamburger. And that is always doable except when the original variable have support on at least 3 points, and the reason is that if you have the support on 2 points only, then the first four moments write down this variable uniquely. It is just a system of equations you have to solve. So in that case, there's nothing to couple with, and then you need this assumption. And you can use the same argument to prove this universality for the K correlation function. Now, later on, it turned out that you can even avoid this assumption of 3 points because there's a reason of Erdős and Yao and co-author show that you can extend Johansson theorem to the case that actually the Gaussian part doesn't need to be a constant, doesn't need to be 50%. It can be just n to the minus epsilon %. And then you use this with a variant of the four moment theorem and then remove this 3 point assumption. So it's just a joint result with this other thing. Okay. Yeah, so for the local version now we also have very general result. The universality of the Dyson kernel here, so you look at the local, this local K correlation function, and you take a test function and you integrate, and you can have it going to what you expected. And the only assumption again that you need is not, so the first moment is 0, second moment is 1, and it have about say 1,000 moment. That's it. It is very close to a conjecture of meta. So the classical book on random matrices is the book of Beta written in the 1960s. It is a very interesting book in the sense that it doesn't have any theorem or lemma in it. So it's just a book writing continuously. And the only thing which is officially stated, there are 2 conjectures on page 9. And this is one of them. Well, the other one is the GOE case of this. And here the only thing we miss is that he doesn't even assume that the C moment bounded. He just assumes first and second moment. Okay. And so let me mention that, I mainly focus on the Wigner model, but the entries in the method doesn't require anything to be real or complex in particular. And even in the complex case, it doesn't require the real part and the imaginary part to be independent. So it's very general. And also, it's holds for the random covariance matrices as far as at the 2 sides of the matrix are comparable to each other. Yeah, so let me, in the last, say, 10 minutes or so, or 15, describe a few ideas about the proof. Now, it is a long proof, but it's quite a long proof, but it starts with a very simple idea. Okay, so, well, let's say we take the case that we want to study lambda I, and I call it x, right? So we want to know the distribution of the variable x. So namely, just the probability that x belongs to some interval. And by definition, it is just the expectation of the characteristic function of this interval. And what a lot of people do here is that we replace this characteristic function, which is a 0, 1 function, by a smooth bump function. So, and then you don't have the exact identity anymore, you have something approximate. But we take things going to limit anyway, so it doesn't really matter. And the huge advantage when you smooth out the characteristic function is that you have a Taylor expansion of the function in question, right? It is a differentiable function, so you can take this. Right. So the next is an important idea. It is a variant of the Lindenberg method in probability. So Lindenberg used it in the 1930s to give another proof for the central limit theorem. And the idea there is the following. The central limit theorem saying that you add random variable divided by square root n and you want it to go to normal. So if the variable are Gaussian in the first place, then they are nothing to prove, right? Because sum of Gaussian is Gaussian. So what he does is that, well, you started with anything, say sum of Bernoulli, and you change the random variable one at a time from Bernoulli to Gaussian. You have to change it n time, and so each time you measure the impact on the sum. So if the sum of the impacts of n changes is negligible, then you prove the law, right? And here we will apply this idea for the matrix. Now, of course, here it's much more complicated because we talk about eigenvalues, which is nothing like the sum of the entries. It's much more complicated function that you cannot even write down. But the idea does work. So actually, so what you do is that, okay, so we start with one random matrix, and the other one is an prime, right? So we want to say that the law of an is the same of the law of an prime. And so what I do is that I look at the entries, I freeze all of them except one, and I'm going to change that one. So let's say that I switch the entries of the place PQ to the prime version of it. Right? And I want to show that this impact on, say, the particular lambda that I am interested in, say lambda n over 2 or lambda 1, whichever I want, is negligible. Okay? So let me simplify the notation now because I fix I and I also fix P and Q. So let's say lambda is lambda I, Z is zeta PQ, and so on. And okay, so I want to measure, I want to see the difference between the distribution of lambda and lambda prime. So I use the bump function idea before and measure the difference between these two expectations. Okay. Now, yes, so it is a function in terms of lambda. But if I fix all the entries except Z, then actually lambda now is a function of Z, only Z. Right? And nothing else. And so I can write it down as actually a function of Z. Right? And as I already mentioned, we have smooth functions, so you can do the Taylor expansion here. So you write down the Taylor expansion in terms of expectation. Right? So you will have matching terms like this. Right? So you have f doesn't change, so what you really subtract is z and z prime and so on, z square and z prime square. So if the first 4 moments of Z and Z prime match, then actually this term cancel, this term cancel, this term cancel. The first 5 terms will cancel. Right? And the only thing you need to care is the the 5th term, right? Which will measure the difference. And it will also show you why you need the 4 moment assumption in the theorem. Right? So the main lemma number 1 of the proof is that you show that the derivative go down by a power of n every time. So if you take the 5th derivative, it is something like n to the minus 5. Okay? And since we already talking about the scaling up of this matrix by square root n, then actually Z will typically have order square root n. So Z to the 5th will have order n to the 5 half. So if you look at this term in the Taylor expansion, this expectation is n to the 5 half. But the derivative go down as n to the minus 5. So actually the difference will be n to the minus 5 half. Okay? Now why do you need n to the minus 5 half? Why don't you just do 3 here? If you do 3 here, you will have n to the minus 3 half, which is also going to 0. But the answer is that I have to do the swapping n squared time. So you need some power that bit 2. And that is the first place when it bit 2. And that shows you why it is the 4 moment theorem, but not 3. Okay, so that is the main lemma number 1. Okay, so proving it is a long story, but even after proving it, you have a big problem, which is usually when you do probabilistic argument, is that with the conditioning. Right? So what did we do? We freeze all the entries of the matrix and change 1. But if the entries you freeze are very bad ones, say they are all 0, then actually a lot of things property has been destroyed by in this particular case. So you have to freeze it, condition on that, okay, the rest of the entries are nice. Okay? So it is hard to say what is nice, but let me tell you what is ugly. So ugly is something like this, that you have 2 eigenvalues which are very close to each other. And okay, so what very close mean is that, okay, we use the scaling up here. So we know that the consecutive eigenvalues will have gap 1 between them, uniquely, unit gap. And so close means that they have some negative power of n gap between them. And then the main lemma number 2 saying that if you look at any gap, any index I, the probability that they are abnormally small is going to 0 with n. It's something like n to the minus 100. Okay? So this means that bad event doesn't happen rarely, doesn't happen frequently.
This is the n in the tail also?
Yeah, that's the n in the tail and the n in the probability.
The tail also in the first one.
Yes, the tail is easier because actually the normal gap is bigger than the gap in the bulk. Okay, so that's main lemma number 2, and this one is quite technical, but it has some nice idea in it. Okay, now, however, well, we see that we prove this thing go to 0, but it's only n to the minus 100. And it can be improved, but by a theoretical reason, it cannot be better than n to the minus half. And it can be n to the minus half, so it can, we have to stop there. And here the trouble is that, okay, but you have to do this swapping n squared time, right? So if you do the union bound here, you are doomed again. Because the bad event will happen n to the 3 half of the time, and okay, that's too bad. So the main lemma number 3 allows you to actually to put the bad event into the function f, which we defined at the beginning, this f. And then it means that the bad event, we have to bound it only once. You don't have to do it, you don't have to do the union bound. Okay. And finally, the last main lemma is something I am quite fond of because it says something quite unexpected. It is about the Cauchy interlacing law, and it is needed when we talk about eigenvalue near the edge of the spectrum. The Cauchy interlacing law says the following: if you take an n by n matrix, a Hermitian matrix with eigenvalue lambda I, and you take the eigenvalues of the principal n minus 1 matrix, then the eigenvalue of the later interlace the eigenvalue of the big one. Okay? So namely that lambda 1 is less than eta 1 less than lambda 2 and so on. Now, you look at the typical gap between two consecutive eigenvalues, which we know that is of order 1, say, in the bulk, right? So, and this guy is trapped between them, so actually the distance between eta I to lambda I is also bounded by 1, at least in the bulk, trivially, right? But we know that the density function go to 0 near the edge of the spectrum, so that means the distribution, the eigenvalue occur very rarely there. And so the gap between the consecutive one become bigger. Right? It takes a long time between you get lambda 2 after you see lambda 1. Then you take, say, lambda n over 2 plus 1 after lambda n over 2. Right? And so actually if you compute it, you will see that lambda 2 minus lambda 1 is not 1, it is rather n to the 1/3. And that is why in the Tracy-Widom law you have to normalize with n to the 2/3, and you also that is n to the 2/3 in the, well, sort of appearing in the longest increasing subsequence problem. Okay. Now what we discovered there is, okay, the interlacing law is a deterministic theorem. It doesn't matter that you take random matrix or not. But the interesting thing when you take random matrix is that when you take it, the law is biased. So namely that although this guy is supposed to be between the two, it is actually glued to the left-hand side one. So namely that the difference between eta I and lambda I is still of order 1. Doesn't depend on this thing to be quite huge. And it is something we discover by, well, I mean, this by a theoretical reason that, okay, if we want the theorem to be true, this thing should be true. It's very hard to discover this by numerical experiment because, first of all, we don't think of it. Second, that, well, at this phi scale, it's very hard to really see the differences. Okay, and so, yeah, let me finally finish this talk by mentioning the, yes, it's, and then, yeah, so each lemma has this old story, but the nice thing is that this combines a lot of tools that we learn. Well, we have been doing this random matrices project for a long time, and then at the end, that every single tools we learn that actually come up in some sense. So it's, it depends quite a lot, as you already see, perturbation theory and matrix analysis. So it relies on linear algebra very heavily, probability, and yeah. So the important technique here is a Steichis transform technique that people, actually the statistic people do a lot. And very heavily on sharp concentration is used in every single lemma. An idea, combinatorics idea of boosting, well, which I probably, yeah, maybe I explain this boosting a little bit because it's something unexpected.
I have a question.
Yes.
In your treatment, I think the first treatment, do you adapt to use the work of Yao et al. In the local weakness? Do you need that, or have you circumvented that? Are you using any of the earlier work from 2 years ago?
Yes, we actually, let me go back. This.
Could you explain briefly how you use their work?
Yes, so. Yeah, let me explain that later after. Okay, so yeah, so yes, and then yeah, I will explain this boosting as well and and a lot of tools from high-dimensional theory, geometry. So there is a parallel work of, Erdős, Yao, and Coulter. But before the work we did in universality, they did a lot of work on the rate of convergence to the semicircle law. Yeah, and even before them, there are a lot of people did work on rate of convergence on the semicircle law. And what they get is a very good rate of convergence. That's something like n to the minus 1 plus epsilon, which is useful here. And I don't need the result specifically, but we need the idea in that work of rate of convergence. And the idea is that if we want to measure the rate of convergence, then what you really want to measure is the difference between the Steichis transform of the two measures. Right? And that was done actually by Bai and other people long time ago, but they have a new way to look at it. And so Bai can only do 1 over square root n, and Erdős and Yao and people can do 1 over n to the 0.99, say, and they need an extra idea there, and that was very important to us. We do use that idea in the proof of this, because the rate of convergence is important there. And on the other hand, they relied on, the new thing in this lemma we need to put in is some concentration result from Talleyrand that simplified the whole thing quite a bit, and also remove the smooth condition that they require. So one combinatorial thing that, of course, this is where I came from, that I like a lot is combinatorics idea is going into this proof of this second main lemma, that actually is, you say that the gap is being small is unlikely. And so the idea here is, okay, we know the interlacing law, right? So we know that the principal, the eigenvalue of the principal matrix interlace. So for a moment, if we know that, say, there are 3 eigenvalues of an glued together, say lambda I plus 1, lambda I, and lambda I minus 1 are close to each other, then actually you can know that eta I and eta I minus 1 are close to each other just because they interlace. What we could do is that to do the thing backward. Namely that if these two are close to each other, and actually now we can prove that there are 3 eigenvalue eta, which is eta I plus 1 and eta I minus 1 are close to each other. So it's an interlacing law backward. Right? So, and if you do it several times, so you start with 2 close to each other, then you get 3 close to each other, then you go to 1 minor down, you get 4, and for, say, after log time applying this, you will have log n eigenvalue which are very close to each other, and then sharp concentration jump in and say that, okay, this cannot happen. And that is the idea of proving this. Okay, thank you very much. Yes, so actually we had, that's the good point. You modify the proof a little, and it say that if they don't match exactly, let me go back to that slide. Oh. Yeah, if they don't match exactly, but the difference between, say, the moment of zeta and the moment of zeta prime is negative power of n, then you still have this result, because you see this that will affect only this. Yeah, and then, right. And then, yeah, that's why we can use this together with the result of Erdős and Yao here, because they have some result that refine the Johansson result by taking, say, the Gaussian part just to be a negative power of n. Doesn't need to be 50%. So that's.
What type of generalizations can you treat from Wigner? Can you remove the independence of the...
No, that is, it is very, yeah, that should be the next big question, but we don't know anything about about dependent entries. So, yeah, the toy question that I usually mention is, yeah, you can think of the, say, take the Bernoulli case, but -1 case. This is basically the adjacency matrix of the random graph. Now you do the following game, right? You generate a random graph, but you condition on it to be, say, regular with degree n over 2, right? So if you generate something and it's not regular, throw it away, keep only the regular one, and look at the adjacency matrix of that. And I don't know anything about that, except the semicircle law. Yeah. For instance, we don't know that it contains 0 in the spectrum or not. Yeah. Yes?
No?
What if you take like circle and drop it?
Yeah. Well, the circular law is not so important because we can do mixture. Oh, yeah, that I don't know. Yeah. So anything that, yeah, that is beyond this independent and normalized entries, that is still open.
Entries independent but not symmetric.
No, symmetry is never important. The only thing you need is mean. Yeah, the mean is 0 and variance 1.
Non-symmetric means the matrix is not symmetric. It means that the spectrum is not
This
real.
is the circle that you mentioned.
That is the random covariance case, right?
Don't look at the Wishart case. Just take a square matrix, but not symmetric.
Right.
With independent. So the eigenvalues are not real anymore.
They are complex.
They're complex.
Yeah.
So there's something called the circle law.
Yeah, we proved that too, but that's the only thing we know. We only know the global.
Global. So you
Yeah.
don't know anything beyond.
No, and the global is hard enough. The global was also open for quite a few years. Yeah, I don't know anything local there yet.